So I talked about optimizing the Mandelbrot set program. And here's what I did is I recognized that I could create a lot more concurrency for my scheduling to work with if I put a collapse clause on that central loop. So I put a collapse 2 there. And then I set schedule runtime, because I didn't want to recompile every time I tried a new schedule. So I put a schedule runtime there, compiled it, and then I just export OMP schedule equals, and then I would put the text I would put in that schedule, dynamic 100. So it let me quickly try different ones. And so you could see I went from the default 0.48 seconds. I did the schedule dynamic 100 to 39 seconds, but if I did the collapse 2 and schedule dynamic 100, I got it down to 34 seconds. So being able to quickly try different things, the fact of the matter is there is so much complexity in a system, from the cache hierarchy to the way the cores are organized to the memory controllers on a chip, the NUMA features of the system. It's very hard to a priori decide, yeah, looking at this code, I think this would be the best schedule, and yeah, just to be the best. In practice, you try different things and use what works best. So that's why this schedule runtime can really be handy when you're experimenting with different algorithms and you just want to try a bunch of different runtimes. So, and there's even more. There's a lot more you can do with the Mandelbrot exercise. It's just a fun one to play with and try and see how fast you can make it run. At any rate, what I want to do is say a little bit more about synchronization, give you an exercise with locks, because I think that's the next big synchronization construct to know well. And then I want to leave 45 minutes at least to talk about GPU programming. But then again, I mean, none of you want to write GPU code. I mean, how many people want to write GPU code? I mean, ew. Yeah, so I'm an anomaly at Intel. I started working with GPUs in 2006 and worked directly with Ian Buck, who's the father of CUDA. And Ian Buck, myself, Aaron Lafon, Afi Munshi, we started OpenCL. And OpenCL was a portable CUDA. So, we learned very much from Ian Buck's graduate work at Stanford, his work creating CUDA, then we all came together and generalized it and came up with this thing called OpenCL. So I've been heavily, heavily involved with GPUs for a long, long time. So back before GPUs were cool at Intel, I was working on GPUs. OpenCL took the attitude of you wanted to write portable code and you would do whatever it took to get portability. And so we did that by exposing everything. So you can go in and start your program up and say, well, what GPU do we have? What vendor does it have? What are the characteristics of this GPU? How many work items? What's the warp structure like? And so after 2 or 3 pages of all this preliminary code, discovering the system and setting things up, you then say, OK, call a kernel to add 2 vectors. So, and my friend Bill Magro, who's now at Google, teased me once in a public gathering where we were talking about OpenCL. He says, well, no human should touch OpenCL. And I had to tell him that, yeah, that was our feeling as well. That with OpenCL, we were writing a low-level runtime infrastructure that's portable, written in C. And the idea is that humans would have higher-level languages on top of it that they would write. Okay, what's an example of one of those high-level languages? Later in this program, you're going to learn about something called SYCL. And SYCL was written originally by OpenCL people to create a C++ high-end interface to OpenCL. So really, really cool, wonderful stuff. So GPUs, yeah, I've really been into GPUs. So I'm very excited that we've had in OpenMP for a while, we've had constructs that allow you to program GPUs. And so I want to leave at least 45 minutes for us to talk about that. So off we go. Let me say a little bit more about synchronization. So we've talked about critical and barrier. And for basic OpenMP programming, that's enough. But if you start getting to more complicated problems, you're going to need locks. Those come up. And you'll need atomic. Those are the big ones. I still stand by my statement, you should never use a flush. So, and depending on the time, I'll give you some examples of what happens when you start using flush. So, let's talk about atomic. Atomic is an old concept. For those of you with more of a computer science background, you already know it well. An atomic operation is one that cannot be perceived as being in an intermediate state. It either hasn't happened or it has happened. You can't observe the intermediate. So that's the classic meaning of atomic. So look at this code right here. Pragma OMP parallel. It's, kind of just, I'm going to create this private variable B. I'm going to call a function that's going to return B. And then I'm going to do some big ugly thing to compute and park the result that I'm going to accumulate in X. And I'm going to put an atomic there. Kind of looks like a critical, doesn't it? Actually, not. Atomic is much lighter weight. Atomic does one thing and one thing only. It protects the update to X. It's equivalent to this. It doesn't protect the function computation. That function computation will still occur concurrently, unordered. It's as if you do that function, assign it to a temp, and then do the atomic update to X. So be careful. Some people think I can just replace a Pragma OMP atomic with a Pragma OMP critical, and it's not quite true, because the atomic just protects that update. But when you study the low-level details of managing concurrency, atomic operations are critical because, and it's that statement I said earlier, an atomic operation cannot be observed in an intermediate state. It has either not happened or it has happened. Now, what we've done with OpenMP as of 3.1, the original atomic I just showed you is all we started with. And that's not quite enough. So there's a set of operations that commonly happen with atomic. And the thing is, these correspond, if we were doing a hardware design lecture, looking at instruction sets, there are instructions in the instruction set that correspond to these operations. Because if I'm dealing with managing concurrency at the lowest level, this stuff's critical. So there's an atomic. We now take a clause for what kind of atomic? Atomic read, atomic write, atomic update, atomic capture. And if you think about these words, they kind of make sense. The Pragma OMP atomic read precedes a statement that reads a variable v from a memory location x. So that's what Pragma OMP atomic read. So the read of that variable is atomic. It can only be observed as having completed or having not happened at all. Now, why do I keep repeating this? Why is that such a big deal? Why am I saying as if it's some deep, profound thing? Well, because if you're writing synchronization protocols by hand, and you are trying to define the ordering of events in concurrent threads, this is how you do it. You look at these flags, you look at these variables that tell you the state of the code, and I can now control how that state is exposed between pairs of threads, not just collectively across all the threads. So if I'm implementing a concurrent data structure, like a concurrent queue, a concurrent hash table, a concurrent, go right on down the list, these are the things I need to do it. So I have this atomic read, where I can read a variable or not read it. I have an atomic write. So I have an expression, and I'm going to assign that expression to a variable and do it atomically. And so now if I want to establish temporal relationships between threads, I can use these. Now, I'm going to introduce a little piece of jargon. I'm talking too much. I'm sorry. In reasoning about multi-threaded code with concurrency, the phrase we use is, did this happen before this? And literally it was inspired by people in computer science in the 70s. They were inspired by their understanding of special relativity. The idea that really one way to talk about Einstein's special theory of relativity is there is no global clock. That, you know, your clock is a local thing that's tied to your inertial reference frame. And therefore, in reasoning about simultaneity, you can't refer to a global clock. You can only compare individual clocks in different inertial reference frames. Well, if you stop and think about a massive distributed computing system, it's in the same position. There is no global clock. I have this system running here in Albuquerque, and you know, its CPU clock says this, and then there's a system running here down the road at Argonne near Chicago, and its clock says something like this. I can use a GPS system to synchronize those clocks, but even by the nanosecond cycle times of a computer, those aren't going to be the same. So if I'm thinking about ordering events, I can't refer to a global clock. So I have to use these atomic operations to establish a happens before relationship. And that's the language they use. You know, I can't say that these all happened at this time because there's no global clock, but I can say that that read happened before that write. And as long as I can make some key happens before relationships, I can build up all my more complex synchronization protocols. Phew, do you want to write that kind of code? Some subset of you in this room do, all right? And you are very important people because most of the people in this room don't want to, but you'll need that from time to time. Okay, so you have the pragma OMP atomic capture. And I don't want to spend too long on this because unless you start writing code with this stuff, it doesn't make a lot of sense. But there are times in synchronization protocols that you're writing that you want to both do an operation and capture its value. And that's what the pragma OMP capture does. It only works with a certain subset of statements, but it allows you to capture a value and save it and then do the increment. What I do want to talk about in a little more detail and actually have you write some code as an exercise is locks. Okay, using atomics to build low-level synchronization protocols, using atomics to build asynchronous concurrent data structures, I put that in the category of a computational scientist needs to know that stuff exists so they can ask the person who's going to implement that for them to do it. But locks, you will need to work with sometimes yourself in more complicated code. So let's talk about a lock. In lock, I can define, it gives me fine-grained mutual exclusion. So remember, a critical section gave you the ability to define a section of code that only one thread at a time would execute. Okay, a lock gives me a fine-grained way to do that. And you'll see in a moment what I mean. So I can have a simple lock. So I have a lock variable. It's of a lock type. I initialize that lock variable with OMP init lock. And then I set that lock. Now, if another thread tries to set that lock after me, it's blocked. So locks give you mutual exclusion, but you have more control. So if thread 1 sets the lock, and then thread 2 tries to set that same lock, and it's already set, thread 2 will sit and wait. And what will it wait for? It will wait until the initial thread unsets the lock. So there's initialize the lock, there's set the lock, there's unset the lock. Now, sometimes what you want to do is you want to look at a lock and say, is this lock set yet? Do I really want to block myself waiting if it is set? Maybe I just want to test it. And it'll tell me, you know, test this lock. Is it set? Yeah, it's set. Okay, I'm going to go do something else. and then I'll go back and check it later. So that's what OMP test lock. It returns immediately telling you, is this lock set or is it not? And then, of course, when you're done, you need to reclaim the memory, and that's what you do with the destroy lock. And I'm not going to talk about it at all, but there are these weird things that I personally will never use called nested locks. And they exist. That's all I'll say. I mean, if I have code that sets a lock and it needs internally to set a lock, I've now nested locks. And things get really ugly. That's in the category of if you feel you need to write that kind of code, don't. All right. So here's an example. So what I'm going to do is I want to count the odds and evens in an input array. So I'm going to have n random values, and I want to maintain a counter for how many are even. I want to maintain a counter for how many are odd. And I want to do this race-free in parallel. All right? So the way I'm going to do this is I'm going to create two different locks, odd lock and even lock. So I have OMP and knit lock T is the type. So OMP lock, I'm sorry, odd lock and a knit lock. All right? I'm then going to initialize each of them. OMP and knit lock, odd lock, OMP and knit lock, even lock. All right? So now I have my parallel region, and I'm going to go through, and I'm going to grab a value of that random array x. I'm going to truncate it so I have an integer, because even or odd doesn't work with reals. So then I check, is it even? If so, I want to increment the even lock. Is it odd? Then I want to increment the odd lock. Okay? Now, could I have done this with a critical section? Yeah. But I can do this with a lock too. But the lock structure can be a lot more powerful in that I can have hundreds of locks. And because they're different locks, they're not conflicting. You know, when I'm checking the state of even lock, I don't have to look at odd lock. So in the case of just two like this, maybe I could have done it with critical sections. But keep in mind, maybe I have 1,000 locks. And so it can make a big difference if when I'm looking at the state of a lock, I just look at the subset that are touching the even lock. I don't have to look at the ones doing the odd lock. All right? So this gives me a way to have this fine-grained mutual exclusion. And if you write enough multi-threaded code, you are likely to run into a case where you want to do this. That's why when I have time to go beyond, and you guys, by the way, are an excellent group. You went much further than people normally do. I normally don't get to this material. So the fact that I'm covering this now is good. You know, reach around and pat yourself on the back. Just go ahead. Some of you are really flexible. You can just get right back there and just really pat. Okay. Good for you. All right. So this is locks. This is kind of like, you know, there's the common core, and then there's the next layer just beyond the common core. This is a key part of that. So here's an exercise, and I'd like us to spend like 15 minutes doing this. All right? I have a file called hist.c. That's histogram.c. And what it's going to do is it's a quick and dirty way to test a random number generator. And what it's going to do is it's going to look at a randomly generated array, and it's going to assign them to bins. It's going to build a histogram. And if I have a uniform random number generator, when I'm done, I better have about the same number of numbers in each bin. And looking at the variation across bins can tell me how uniform was that random number generator. So it's like the quickest, dirtiest test of a random number generator. And by the way, you all know, don't ever accept a random number generator as is. You always test them, right? Right? Yeah? I have a whole lecture I give on random number generators because it's amazing how much bad science is done with them because people don't understand them when they go parallel. So always be skeptical of any random number generator. This is the easiest test to do. So build a big random array, And I think in the HIST program I have that. I'll check in a moment. You may have to use my, I might have a random number generator you have to link in. Well, I'll check in a moment. But the idea is, think about everything we've talked about today, and I want you to focus on building this random number generator, building the histogram in parallel. And only focus on timing the part of filling the histogram. And I want you to do it in parallel. And of course, think about what we just talked about. All right? So, go. And I will check. I have a random number generator in random.c. The function prototype is in random.h. So when I compile this, you need to compile hist and random and link that random in there. Or if you have your own random number generator, go ahead and use that if you have your own. The essay was profoundly impactful on my thinking about end-of-life issues. You know, it's basically, I don't want to outlive my brain. And statistically, your chances of outliving your brain start going down, start going up really fast past 75. So it's not commit suicide at 75. It's like after 75, don't do aggressive life-extending health care. That's his point, and he walks through. So it's fascinating. I highly recommend reading it. But what I didn't realize is Albert Einstein died at 76. He was taken to the hospital with an abdominal aortic aneurysm. There are surgical treatments for that. And he said, no, this obsession with extending life endlessly makes no sense. I've had a great life. And so he refused treatment, even though there was a treatment. And but how long would he have lived along? So Albert Einstein, the trailblazer, hero of physicists far and wide, was a leader in that thinking as well. So at any rate, let's talk about not medical ethics. Let's talk about OpenMP. So you may not have time to finish it, even though I'm going to describe a variety of solutions. You learn a lot by piecing the final elements together yourself. So on your own, play around with this and see where you can take it. But I'm only caring about filling that histogram. And of course, I can put a pragma OMP critical. I can, throw a sledgehammer in the middle of it. And oh my God, that's going to potentially be devastating to performance, because I'm putting a critical section in the middle of a pretty fine loop, of a loop that's not doing a lot per iteration. So that's kind of rough. But I can also do this. And this is the version of it I think it's important for you to play with on your own. So I need to initialize the locks. And notice I can do that in parallel. And I'm creating a lock for each bucket of the histogram. Okay? Now, this is a little bit radical for a simple problem like this, but there are big problems. And I have an example of one in a few slides, which I won't go through today with a genetic algorithm. But there are algorithms where you're having complex data structures that can be very large, and you really don't want to have synchronization over pieces of it impacting globally the whole structure. So this trick of I have this data structure and I will have an array of locks so that I'm locking at each element of the data structure, not the whole structure, is how you would do this. And so you can initialize an array of locks, and now I go through, and now I have my mutual exclusion lock is at the level of one lock per bin. So this is an example of where I would use fine-grained locking to have control over the mutual exclusion synchronization. So yeah, the critical was easier, but depending on the situation, this can be a lot more efficient. And then reclaim your memory when you're done. It's by destroying the locks, which I also do in parallel. Now there's another stunt I can use. So I can do pragma OMP parallel for reduction. So I've allocated this array hist and zeroed it. Okay? So now I just do the reduction, the array reduction. Really, really easy. Isn't that beautiful? and compare the runtimes. So serial 0.0019, critical 0.079. The locks per bin, I got it down to 0.029, so it did a lot better than the critical. But what I loved and was so just gloriously delighted when this happened is by going to the reduction with the reduction on the histogram array, I beat the serial time. So it's pretty cool. So this is another exercise to play with. It's instructive to experiment because in the course of a professional life with OpenMP, you will come up with times when you want to lock, when you want to have mutual exclusion but finer grained control. So now I'm going to jump a little bit. Okay. Remember when I told you about the flush, and we talked about flush. So there is a common synchronization pattern, not so common in OpenMP, but in writing multi-threaded concurrent code of a producer-consumer pattern. I have one thread producing results that another thread is going to consume. And what I want you to remember is in practice, this wouldn't be an individual produce, consume. This would be a pipeline of production and consumption. So think of it, this is the heart of a pipeline. And I want pipeline parallelism, therefore I want these producer and consumer updates to happen in parallel. So this is basically a microscopic step buried in the middle of a large complex pipeline parallelism code. So I'm going to basically fill a random array. So I'm going to produce an array, and then I'm going to consume it by summing that array. So I have a producer of an array, I have a consumer that does a sum. And I want to do that so that the consumer waits until the producer is done. So that if it's a pipeline, I can have things happening in parallel. And so I'm not going to walk through all the level of details, but I'm just showing you how I can use the sections and section to create one section that's the producer, one section that's the consumer. And I can have a spin lock. So I have a shared variable flag, and I initialize it to 0. And when my producer's done, it sets the flag to 1, so that the consumer is spinning on that flag. This is a spin lock, is spinning on that flag so that when it's no longer 0, it knows that one's done, and off it can go. All right? Looks pretty simple, doesn't it? This is a spin lock. This code won't work. It won't work because of flush. Remember, compiler can reorder instructions. Nothing stops the compiler from doing the flag set 1, then do the fill array. Okay? There's all sorts of reorderings. So if I were a glutton for punishment, this is the correct code. This is why I say you do not want to write point-to-point synchronization with explicit flushes. You just don't want to go there. So I just want to show you how I got to fill the array, then do a flush so that it can't move the set of the flag in front of the fill. Compilers reorder instructions. You have to take that into account when you're doing this kind of coding. And so I need to make sure that it finishes A, it flushes the result to make it visible, then it sets the flag. And it has to do that as an atomic so that it can only be observed as done or started. Are you asking a question or just stretching your finger? Okay. So I need those stupid flushes in there. And then inside the spin lock, so a compiler will look at a flag and go, oh, that's a variable you're looking at again and again and again. And oh, it's not being changed. So it'll promote it to a register. That's just what compilers do. And most of the time they do that, you want them to do that. All right? So it's a good thing for the compiler to do. Well, I want to tell it, don't do that. go back to memory and refresh that flag. Come on. So I have to put within the while loop, reflush the flag, and then do an atomic read to match with that atomic write up above. And then when it's done, and I really do get that it's changed, then I do a final flush to really make sure that this sum is not moved up, and then I'm going to get the final value. Don't you want to write code like that? Now, I want to leave you, though, that this capability is built into OpenMP because when you're building complicated concurrent data structures, you may need to do this kind of shenanigans. It's just no one in this room write this code. Okay. Now, for the pairwise synchronization, we added something called sequentially consistent atomics. And we've added a number of capabilities, acquire and release memory orders. We've added stuff in OpenMP so that you don't have to write that kind of messy code I showed you in the other slide. And so using the latest and greatest in OpenMP, we have sequentially consistent atomic and writes. So the sequentially consistent means that your instructions are in an interleaved order, but every single thread will see the same order. So it takes care of that compiler reordering for you. And it implies a flush. So now I can just do an atomic write, sequential consistent. And I can later, inside my loop of the spin loop, I can do atomic read, sequential consistent. All right? So I just want to make you aware that this stuff is buried in OpenMP. So if you ever find yourself needing more complicated synchronization constructs than you can do with a lock, a critical, or a barrier, these things are there for you to learn about and use.